Welcome back, students, to another exciting episode of the Flipped Classroom. Today we'll be doing our video lesson for 851. We're going to be talking about the dot products in space, the final frontier. Well, it's almost final frontier. We got one more lesson to go. So this is a pretty simple idea. This won't take very long, I don't think. All that we're doing here is extending the idea of the dot product from 2 dimensions into 3 dimensions. And we already played around with 3 dimensions a little bit in the last lesson. And so if you've got your straws available, that would be good for visualizing some of these concepts. See, we've already used the dot product for physics. We've done that with work problems, and we've found vector projections and multiplied those things together when we were dealing with work problems. So those work problems, we always kind of idealize them as working on only 2 dimensions, and like height and depth, height and length. But now we're going to think that maybe that would happen in 3 dimensions. Things might be slanty-wise, because that's the way the ruler works. Also, we've used the dot product to find the angle between 2 vectors in component form, which we found that was a better way of doing it than breaking things down into components and then reassembling them, especially if none of the vectors end up being along the axes. And so this also happens in 2D. You can think of that taking your sheet of paper and that being in 2 dimensions and then tilting it either towards you or away from you, and now you've got something that's in 3 dimensions. And that happens in the real world too. The angles, like for example, between the parts of a molecule, the bonding angles. We've talked about in chemistry how the water molecule has a kind of a weird angle there, or if something's a tetrahedral model like methane, it has weird angles too. So we would have to think of that in 3 dimensions instead of 2 dimensions. Okay, so that's what we're going to be doing here. And again, use your straws to visualize these things, but here's the main key concepts if you didn't write this down from the book already, is that now instead of having just 2 dimensions, we have 3, and we want to treat these subscripts as dimensions. So here's the A vector in its component form, and how much it is in the 1 direction, or the X direction, the Y direction, and the Z direction, the first, second, and third dimensions. We got a second vector here, and also it's in 3 dimensions. So the dot product ends up being just this quantity. Ooh, don't want to move anything around. This quantity right here. The first dimension parts multiplied by each other, the second dimension parts multiplied by each other, and the third dimension parts, and then all those things summed up together. So it's not really that much different than the dot product in 2 dimensions. We add a third dimension and we do the same exact thing. And the orthogonal rule is the same here as well. If we do this in 3 dimensions, we find out that these things are at 90 degrees from each other in 3 dimensions, then the dot product is 0. So that's the same as in 2 dimensions as well. Okay, that's pretty easy, right? We're just adding one more thing. We're doing multiplying and adding. That's all that we're doing here as far as the math goes. Now let's look at the examples. The first example is asking the question, are these 3D vectors orthogonal? And so the first guided practice gives us these 2 vectors, u and v. You can also look at the examples for a minute. Go ahead and pause, and I take maybe 1 minute or 2 minutes to look at them and see how they work. And then I want you to go ahead and try guided practice number 1 here. Write it down on a piece of paper that you can bring to class where you can check these things. But I'll give you the answers here in just a few seconds. Go ahead and pause. Look at that the example. Try the guided practice. And then when you're ready, you hit play again. So you can see my math there. Did I do this right? Well, I did get 0, and so these are orthogonal. If you want to try to picture them in 3 dimensions with your straws, you can see that it would have been a good guess, wouldn't it have been, if you'd done 3, -5, 4, and 5, 7, 5 in 3 dimensions. You'd see, yeah, it does look 90-ish. So, but that verifies it. It is orthogonal. And there you go, because the dot product is 0. Okay, why don't you go and try this second one here. Same deal. You probably even do it in your head and come up with a number, then verify whether it's orthogonal or not. And there we go. I get a positive number, which it's not 0, so that means those are not orthogonal. And the positive number tells me that I've got an angle greater than 90. Have we talked about that yet? If not, you'll see something about that today if you watch the second video. Let's go on to the last page here. You ready? Ready, 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 ready. Okay, let me scroll up here and get this puppy ready to go. Okay, example 2. What is the angle between vectors? Of course, that's our other question, so we're going to use this version here of the dot product. Magnitude of A times the magnitude of B times the cosine of the angle between them. Or when we boil it all down, we're going to use the inverse cosine of the dot product over the magnitudes. Now, one last thing to tell you here, these magnitudes in 3D, the magnitude of the vector goes like this. Okay, magnitude of the vector is just the first dimension squared plus the second dimension squared plus the third dimension squared, and we take the square root of that. So it's the same thing as what we had before, but we added on one extra piece, no problem. Okay, so that's what we got to deal with here, and let me give you a real example. Guided practice number 2. Okay, so they give it to us in the unit vector formation. So you got I, J, and K there as being the unit vectors, and the numbers in front just represent a scalar multiplier. And so first thing to do is to translate that into our component form. So it's more what we're used to. And this first one is -4, 2, and 1. Now the second one is missing the j part, so that means the j part is 0. So 4, 0, 3. And then this would be the method that I'd take with these. First thing you want to do is just find the dot product. -4 times 4 plus 2 times 0 plus 1 times 3. Okay, the second thing would be to take each one and find the magnitude of each vector using that square root of the 3 parts squared. And be the square root of -4 squared plus 2 squared plus 1 squared, and the square root of 4 squared plus 0 squared plus 3 squared. So, and then write that number down. Keep it as a square root if it's not a perfect square. The third thing would be just plug those numbers in, and then take the inverse cosine of that fraction. So why don't you go ahead and pause and try that guided practice right there using this formula right here. Find the dot product, find the magnitudes, and then hit unpause when you're all done, and I'll show you what the answer is. Voila! Is that what you got, or something close to that? Because you should get -13 for the dot product, and then the magnitudes are square root of 21 and square root of 25. So you take the inverse cosine of that ratio, and you get about 124.567 degrees with 1/10. We get 124.6. Okay, that's that. There is one more thing to do, and that would be just watch another example of these kinds of things in the video that is linked in the description below. Please watch that. You don't need to stop and pause. You just need to watch it and see another guy explain the same thing, but I think he has a 3D vector thing that he's able to show you, which I think is pretty cool. So check that out and try some problems. Bring any of your questions to class. We'll see you then.